In lab, you guys carried out a couple reactions, one where the temperature increased and one where the temperature decreased, and then you had to classify those reactions as exothermic or endothermic. And I don't want you to make the mistake of confusing reactions and phase changes. So we're going to take a pretty in-depth look at what the difference is and also the similarities are between endothermic and exothermic reactions and phase changes. So let's start with exothermic and endothermic reactions. Remember, in a chemical reaction, we get something new. We get something we didn't have before. In a physical change, we don't get anything new. A phase change is a physical change, and because these processes are different, we analyze them differently. So let's start by looking at a phase change. We've talked about these for a while. It changes, that's when a substance changes between states of matter, this common state, solid, liquid, gas. This requires energy to be absorbed by the substance or released from the substance, depending on if the particles are going to end up in a more ordered or less ordered state. But it is a physical change, so nothing new is made, and that also means no new energy. Okay, so no new matter, but also no new energy, or different energy, I guess. So no new matter, no new energy. All we have is thermal energy moving around from one place to another. Whereas in a chemical reaction, we break bonds in reactants, we form them in products, and we do end up with new stuff. We end up with new substances, but we also end up with new energy types. So we're not going to have just thermal energy moving around like in a phase change. We're going to have new types of energy present that we didn't necessarily have before. Now, let's look at an exothermic reaction. Exothermic is exactly what it sounds like. Exo is exiting, thermic is referring to energy, so thermal energy is coming out of this reaction. It is being produced by this reaction. In fact, in an exothermic reaction, thermal energy is a product. Right? It comes out of the reaction. So let's take a look at what's going on. In an exothermic reaction, thermal energy is released to the surroundings, so it gets warmer. We end up with more thermal energy than we started with. But we have to know where that energy comes from. Chemical potential energy is converted into thermal energy, right? In a chemical reaction, we have changes that occur. We started with chemical potential energy, but we end with thermal energy. We started with products, we end with reactants. So right here, this graph is showing me how the energy changes throughout a reaction. The reactants are over here. The reactants started with this much chemical potential energy. If I trace that line through, when we get to the end of the reaction, the products have this much chemical potential energy, and you can see that that's less. So the overall amount of chemical potential energy stored in the bonds went down in this reaction. So out of this is the thermal energy that pops out of this reaction. There is less chemical potential energy, so there is more thermal energy, and as a result, the temperature increases. Now, what's with this little point here? Well, that's the thing called activation energy. That's the energy we need in order to make a reaction occur. Some reactions can gain enough energy just from their surroundings to get this to happen. Other reactions, they need a larger input of energy. If you've ever lit a match, matches don't light themselves. You scrape them across the striker so that they gain enough energy to actually light on fire. If you've ever lit in a propane grill, you know the propane doesn't light itself. You put in a little bit of energy to get that to happen. So this is the energy it takes to break the bonds in the reactants so that they can form new bonds as products. In an endothermic reaction, the opposite thing occurs. So we have the reactants right here and the products over here, and you can see the products are going to end with more chemical potential energy. They end up here. They started down here, so chemical potential energy went up. The products end with more chemical potential energy. But you have to stop and ask yourself, where did that chemical potential energy come from? Well, that chemical potential energy came from the thermal energy that the surroundings used to have. Okay? So endothermic reactions absorb thermal energy from the surroundings so they feel cool. That means thermal energy is a reactant. It's not coming out of this reaction, it's going into the reaction. So thermal energy is taken from the surroundings and pulled into the chemicals and changed into chemical potential energy. That means there's going to be less overall thermal energy. Thermal energy is converted into potential energy, there's less thermal energy. That means it's going to feel cool. You take one type of energy, thermal energy, which is the energy of the particles. They have, the more motion they have, the more energy they have, the more they move, the higher their temperature. We take that energy and we convert it into chemical potential energy, which doesn't involve heat, doesn't make the particles move more. It's going to decrease the temperature. Now, phase changes are different than reactions, but there are some similarities. So in an exothermic phase change, we have particles that are in a high energy state, like in a gas, that change into a lower energy state. They go to like a liquid state. In order to do that, they have to give away energy. The particles have to lose energy to their surroundings. They started with thermal energy, they end with thermal energy, but they end with less thermal energy. The surroundings end with more thermal energy. So in an exothermic phase change, thermal energy is released to the surroundings, but it is not changed into any other type of energy. It's just a physical change. We're not getting anything new. So the temperature of the substance during the phase change itself remains constant. But because it's releasing thermal energy to its surroundings, the surroundings are going to get warmer. Freezing, condensing, and deposition are all examples of exothermic phase changes. Endothermic phase changes, exothermic chemical reactions are different. They do release energy to the surroundings, but it's not energy from the particles, it's energy from the chemical bonds. So when energy conversion occurs, chemical potential energy is converted into thermal energy, that energy is released to the surroundings, increasing the temperature. Explosions happen and are an example of an exothermic chemical reaction. Burning is an example of an exothermic chemical reaction. Now, endothermic is different, right? Endothermic means that energy is absorbed. So in an endothermic phase change, the particles have to absorb energy there from their surroundings. So maybe a solid with its particles in its neat orderly arrangement becomes a liquid when energy is absorbed. But this is thermal energy going in, and it ends up with a liquid which has no order, right? But the particles are close together. They have more thermal energy now. The temperature again remains constant, but there is less thermal energy in the surroundings because it's absorbed from the surroundings, and it increases the energy state of the matter. So we still have thermal energy, it just moved from one place to another. The temperature of the substance stays the same, but the surroundings decrease. Now, melting, boiling, and sublimation are all endothermic phase changes. They all involve taking energy from the surroundings to put the particles into a higher energy state. Endothermic chemical reactions don't do this. They don't put the energy into, or the matter into, a higher energy state. They take that energy and they change it into chemical potential energy. So thermal energy is converted into chemical potential energy, and that means the overall amount of thermal energy is less than when we started. Thermal energy is lost. It's changed into chemical potential energy, and this decreases the temperature of the surroundings and the reaction actually. And when you mixed vinegar and baking soda, you saw the temperature go down because the thermal energy was converted into chemical potential energy.